Okay.
Okay, so I will stop recording and then restart. Oh. Okay. So do you want to go ahead? I'll introduce you.
Yeah.
Our speaker is Mathew Cater Benavides, who will speak on fractional Brownian motion. Go ahead.
Yeah, so as Lisa said, my name is Matthew. I'm a fourth year here at the University of Toronto, and this is the fractional Brownian motion is a process that myself and another audience member here today, Neo Yin, have been looking at as it's been a central object of study for that of our research project this year on coalescing systems, and in particular coalescing systems involving the process of concern today. So just a quick agenda of what we're going to run through today. We're going to start with some motivation of first the classical process, i.e. the standard Brownian motion or Wiener process, on the real number line of a single dimension. And from there, we're going to give a quick review and recap of Gaussian processes, as we're going to use some of the characterizations that they have to be able to quite nicely introduce the process of which we care about. And from there, we're going to give the process, and we're also going to prove and define some of the first properties. So firstly, motivation from that of the classical process. So I'm going to motivate it as follows in a form of a random walk effectively. So first, consider a finite collection of IID random variables. And for those less familiar, we can just think of that as a set of n random data points for right now. And suppose that they all have a mean 0 and that of a unit variance. Okay, so from there we can define what we're going to call a process, and I'll also introduce the notion of a process here a little bit as well, as follows. We can think of it as a random function, right? So what's happening is we're developing a function on that of the unit interval of time. We can think of it as follows. So what we're going to do is chop up the unit interval into n equal pieces, and then we're going to define our process to take the values of our n random samples and then linearly interpolate in between. So what that looks like is this. We're going to chop up the unit interval into these n pieces and plot our random samples, and from there linearly interpolate in between. And so what we're getting is a random function. We can see that for each new set of random data points, x1 through to xn, these linear interpolations are equally as random. So every single plot on this entire function is random. So what we're getting is a random function, or equivalently a stochastic process in time in this sense. Okay, so the idea to model that of the Brownian motion is to take n to infinity. What that's going to look like is adding more and more of these data points, continuing to linearly interpolate in between, and getting a more and more rough path as you go. And it will look like this in that limit. And this is in fact a depiction of a Brownian path. I can pause for questions here.
Are there any questions?
Okay. I will proceed. So with that out of the way, I want to review some technicalities regarding Gaussian processes. First of which, we're just going to fix a probability space and make absolutely no assumptions about it just yet. And from there, we're going to give our first definition of which we're going to deem a Gaussian process. So a Gaussian process is quite simple. It's a stochastic process, i.e. a collection of random variables that's going to be indexed by this capital T set, of which we can think of as positive time. And soon we're going to take it to be positive time. And the only property it has is that any finite linear combination of these random variables is going to be a centered real valued Gaussian random variable, right? So another way to interpret that for those more familiar is that any finite dimensional marginal is going to have a joint normal distribution. Okay. From there, what's nice about the Gaussian processes in particular is that they have a very, very nice characterization in a very specific way. So the analogy I want to draw before I introduce process, or pardon me, this characterization, is that of how we can characterize just the normal density in the one-dimensional case. So when you think of a Gaussian density, there's really only two parameters that are of interest, the variance and the mean. If you tell me two things are normally distributed, then should they share the same mean and variance, you can tell me that their densities agree and are in fact identical. So we want to bring this analogy into the world of Gaussian processes, or equivalently Gaussian random functions. Okay. So the natural way to do that is to still maybe want to talk about the mean and the variance of a Gaussian process itself. In this case, what we actually need is a set of means and a set of covariances, right? And so we're just going to label those all out in this language of functions, right? So we can define the mean function and the covariance function as follows. All the mean function is going to do is take the time at which you're observing a random sample and return the mean of the distribution at that time. And the covariance function is going to take a pair of your stochastic process, a pair of your random variables within the process and return the covariance between them. And the theorem simply states that Gaussian processes sharing the same mean and covariance functions are equal in law. And so these two functions will entirely determine the distribution of a given Gaussian process. So what do we mean by that in particular? I'll actually prove it so that we can see some of the details. So if we fix a Gaussian process xt, and we're going to denote its mean and covariance functions as mx and gamma x respectively, and then we're going to take any choice of finite times, t1 through to tp, and consider a finite dimensional marginal, i.e. the random vector consisting of xt1 up to xtp. Just to be clear, this is an RP valued random variable, and it's going to have a joint normal distribution because this is a finite dimensional marginal from a Gaussian process. And that was part of the definition. So this is all from the definition so far. Okay. From there, we can look at its characteristic function, which is a natural thing to do. And for those unfamiliar with the characteristic function, it's just going to be the Fourier transform of the distribution of the variable, which is, or the vector, if you like, which is going to be a measure on R to the P. Okay, so if we take this Fourier transform, I'll spare you the details of the computation, but it gives what's on the right-hand side there, this exponential thing. And what you can observe is that what sits on the right-hand side only has two real parameters, mu x and sigma x, where mu x is the mean vector, which is going to be given as very literally the vector consisting of the means, as well as the covariance matrix of the random vector, right? And we can re-express the mean vector and that of the covariance matrix in terms of the mean function and covariance functions as follows. So what we're seeing here is that the characteristic function of a given finite dimensional marginal is entirely determined by that of the covariance function and the mean function, right? So now, if we consider another Gaussian process with the exact same mean and covariance functions, its characteristic function is going to be identical as well, right? For that given finite dimensional marginal. Well, we know that if two random vectors are going to have the same characteristic function, they're going to agree in distribution. And so that's all we're leveraging here. So for those who are less familiar with the construction that kind of just happened, the moral conclusion is as follows. Specifying a Gaussian process or a Gaussian random function amounts to specifying a mean and covariance structure on the collection, because any other Gaussian process with the same mean and covariance structure is going to agree in distribution. So the nice analogy to take from that is similar to what we brought up before in the case of the Gaussian real random variable, where you only needed to specify a variance and a mean. So for the Gaussian random function, you only need to specify two things as well. One of them remains the mean, and the other one is now this covariance function. Okay, I can pause for questions again there. Yep, Neil.
I have a question. So, the covariant functions only taken two times, right? But then in the finite distribution might have more than one, like multiple times. So it's not more than two-dimensional. Why is it that if you specify two-dimensional covariance function, then instead of like why is that enough instead of like a higher dimensional covariance matrix?
Well, because those two-dimensional, those pairwise covariances are the entries of the covariance matrix itself. So the entire covariance matrix is just made up of those pairwise things. Right. Okay. Great question.
Thank you.
Okay. So let's continue. I'll throw another definition out there for now, but it actually just simplifies the definition we gave prior. So I'm going to define a centered Gaussian process to be a stochastic process such that any finite linear combination of the variables is still centered Gaussian, or pardon me, is still Gaussian, but moreover that it's centered. So what this is doing is say, take a Gaussian function, pardon me, a Gaussian process, and then just have its mean function be identically zero, right? So this is removing one layer of complexity from that of a Gaussian process. Okay, so we're making no assumptions about its covariance structure at all, just that every single random variable in the collection has zero mean. Okay, with that machinery alone, we can actually give a rigorous definition of the classical process, which is nice. So a Brownian motion, or a standard one-dimensional linear Brownian motion, is a stochastic process that is centered Gaussian, and moreover has this covariance structure given as the mean, or pardon me, the minimum of the two times, right? So as we just saw, to characterize any Gaussian process, it's enough to give a mean and covariance function. And so for that of the Brownian motion, the mean function is just the identically zero map, and the covariance function is given as follows: the minimum of the two times of which you're considering. And what's nice is actually all the other equivalent definitions of the Brownian motion that are potentially more familiar from the context of the random walk or the motivation we gave prior are equivalent to this. That's the kind of amazing thing. So what we see in statements 2 and 3 are the famous independent and stationary increment properties, of which the Markov property can be derived from, as well as the almost surely starting from zero, right? So that's what's quite nice about this. The first definition is a bit more abstract, but ultimately results in the exact same information and intuition about what the process is doing on a physical level. Okay, and the last condition is that it has surely or almost surely continuous sample paths. And what we mean by sample path is fixing a given set of random data, if you like, and then considering the function as we vary time with it, right? Okay. So one thing I want us to note before we move on from the classical process entirely is that the independence of increments are a very key feature in that of the classical process, right? So what we mean by independence of increments is if you can look at the process on non-overlapping timescales, then the net change in one timescale is completely independent of the net change in the disjoint timescale, pardon me, time interval, right? So what that's saying is that the behavior in disjoint segments of time is entirely independent. Just keep that in mind, as that's going to be a key distinction between that of the non-classical case. Okay, so now we're actually ready to give the rigorous definition of the fractional Brownian motion, which is quite nice. So from here on out, I'm just going to take the index set to be positive time. So I'm no longer going to try and define stochastic processes over arbitrary index sets, but instead with just the positive reals, because we want to think of this as time from here on out. So the definition of a fractional Brownian motion can be given in a very similar way to that of the definition of a classical Brownian motion, i.e. they're both centered Gaussian processes, and hence all we have to do is provide some covariance structure for which will entirely determine the distribution of the process. And so that's why this definition is so brief. A fractional Brownian motion of Hurst parameter h, which is going to be an element of 0 to 1, exclusive on the 0, inclusive on the 1, is a centered Gaussian process with covariance given as this. The reason I haven't written the words covariance explicitly, nor the capital gamma function, is here we can kind of just use that neat covariance identity and see that the zero means cancel out. So the left-hand side being the expectation of the product is very literally the covariance. So that's why we've expressed it like this. Okay. So a priori, there's no reason for us to be able to see how this is in any way a generalization of the classical process, right? So that's the first question I want to answer before we start proving some things about the motion itself. So if h is a half, it turns out that the fractional Brownian motion is nothing but a classical Brownian motion. And what we mean by that is it agrees in distribution. And the proof is actually really, really simple. So all you have to do to show something's a Brownian motion, if we recall, is show that it has this covariant structure and that it's centered Gaussian. So if we're considering a fractional Brownian motion of Hurst parameter at half, it's already centered Gaussian. So all we would need to do is compute the covariance and hope that it agrees with that of the classical process. And it does. So if you take a half up here, and you suppose that S was less than T, this immediately simplifies to S, of which serves as the minimum of S and T. There's, of course, no loss of generality on the ordering of S and T. Okay. So the first property that carries over from the classical process to the non-classical process is a selfsimilarity index. So the classical process features self-similarity of index 1/2. But what we actually see in the fractional case is you have a self-similarity, except it's going to have an index of h now. So for those unfamiliar with self-similarity, you can think of it in terms of the fractal geometry sense. And I've just given an illustration here for the case when h equals 1/2. What this is saying is very literally its title. It's saying if you zoom in, it is similar to itself in a very specific way. So if we actually just look at the equation, what this is saying is if you take some time scaling, i.e. fix some epsilon and scale the time, which is to zoom in or out on the x-axis or the t-axis, then should you account for that with some special corresponding space scaling, i.e. the height, then your resulting process will still be equal in distribution to the fractional Brownian motion. But it's not an equal amount of space scaling. That's something to keep in mind. We're not saying that if you scale time and then scale space the exact same amount that you have the resulting distribution to still agree. We're saying that if you scale time in a specific way, you need to scale space in a specific but different way to retain the distribution. Any questions about that or anything I've said since the last time I paused? Okay. So the proof is really straightforward. And so just going to leave it as an exercise. What you want to do, if you want to show anything is going to be a fractional Brownian motion, there's only two things to check. Is it a centered Gaussian process? And does its covariance structure line up? Well, we can check that it's centered really quickly. You take the expectation of this thing and pull the constant out. And this guy right here is going to be centered. And then if you want to check the covariance, it's a straightforward computation. But you will see, in fact, that if you do this out, that you get exactly this. Okay. Now, another property that carries over from that of the classical process to the non-classical process is the stationary increments property. And so what do we mean by stationary increments in a precise sense? It means that for a fixed S, i.e. a fixed time, and of course, a fixed Hurst parameter that's not equal to 1, that's important here. The process defined as follows is also going to be a fractional Brownian motion of Hurst index h. So to see what this process looks like, this reshifted process, I decided to illustrate it here because I think that'd be easier than me talking about it. So what we're looking at is we're fixing S, and then we're looking at how much S has grown in t seconds later, if you'd like. That's what bt plus S minus bs is going to signify at any time t. Okay. So what I've graphed on the right-hand side is a simpler way to visualize this. If you're just subtracting off this constant, because mind you, this is just a constant for each omega, for each outcome. If you're subtracting off this constant, that equates to just dropping all of what was here down to 0, at least at initial point. And also that is why, that's one of the things that will serve as a sanity check as to why these things could even possibly be equal in distribution. I mean, they both have to start from 0. Okay. So now if we just visualize what lives here, which is the process itself, I plotted that here. So what we're saying is we can view the process's life after time S as a process in and of itself. And it turns out that process itself still agrees in distribution with the mother process, if you will. And that can be very easily intuited. I mean, what we're kind of doing is just chopping a piece of it and then bringing it down to 0, i.e. kind of reshifting it to have the distributions match. but ultimately we're considering a subset in a certain way of the original process. So it makes sense that it's going to agree in distribution. Okay. Proof, again, you can check it's centered immediately by taking the expectation of this and knowing that expectation is linear. So you'll get 0. And then again, if you compute the covariance, it's just a little bit of algebra and you will get the familiar formula. Okay. So I cheated you initially when I proved that when h equals a half, we have the fractional Brownian motion reduced to that of the classical process. Why? Because I didn't check this condition, which was condition 4 of the definition of the classical process. I didn't prove that they had continuous sample paths at the time. I just showed that the covariances matched up and that they were both centered Gaussian. So I'll do that now. The reason I didn't do it then is because it requires a little bit more machinery and I did not want to skip the proof entirely. So continuity of sample paths is something that's a little bit indirect in the sense that what we're going to do is take the process and show that it admits what we're going to call a continuous modification. And before I talk about the definition of a continuous modification, for those familiar with measure theory, what we can interpret this as is taking a process, changing it on a set of measure 0, and having the changed version be continuous, right? So that's a nice way to think of a modification. And very literally, that's effectively what it is. If you take a stochastic process, i.e. an FBM in this case, then you can find a corresponding process for which all the sample paths are continuous and that at every given time, the distribution of the output of these two processes agrees with probability 1. Okay. To prove this, we need a result due to Kolmogorov, which is the kind of the standard way to go about showing continuity of sample paths for Gaussian processes, as well as some more general processes. That result's called the Kolmogorov-Chenstov continuity theorem, often, at least in common parlance. And it's stated as follows. If you take a stochastic process and assume the existence of 3 positive constants, k, p, and beta, such that the following holds, which is to say you can bound the LP norm of the increment above by the amount of elapsed time to the power of 1 plus beta and with some constant sitting out front. Okay. If you can do this, then the process will immediately admit a continuous modification in the sense we just introduced it. So this is not, what's amazing about this theorem, this is not a very intense imposition. To bound the expectation of the increment is not often a big task, especially when you have nice formulas for the variance or other statistical properties of increments. And normally we can indirectly or even directly describe stochastic processes in terms of the distributions of their increments. And so imposing some bound on the expectation of it is oftentimes not too hard to get, but the payoff is quite high, i.e. the continuous modification. And so let's just see it in action. So if we want to prove it, I've stated the theorem up here again, just so we can refer back to it. The proof is 1 line. If you write down the expectation of the increment squared, i.e. its variance, you will get t minus s in absolute value to the 2h. And so that very clearly satisfies this Kolmogorov condition. Taking k to equal 1 and taking beta such that 1 plus beta equals 2h. So the proof is very simple due to this really, really powerful theorem. Okay, so far everything I've proved about the fractional Brownian motion when h is not equal to a half or when it is, has been what is carried over from the classical process, i.e. the continuity of sample paths, the stationary increments, and the self-similarity, although given with a different index, but ultimately these things were all properties of that of the classical process. So let's talk about something that does not carry over when h is not equal to a half. And the first thing is that the FBM is in general, i.e. for h not equal to a half, not Markov. And what we mean by Markov for those unfamiliar is that trying to make predictions or statistical observations about the process after some given time, conditioned on what has happened in the past, is equivalent to making the predictions given the information of only the present. So what this means in just a heuristic sense, so we can continue, is that the process is independent of the past and really only dependent of the present. Okay. So how do we then describe the dependent structure of the FBM, and how does such structure vary with the Hurst parameter? So just to hammer home that point a little bit more, the classical process is motivated from that of a random walk, which is the quintessential example of a Markov process. You're taking a random step at every given time, and it's not being governed by anything that had happened prior, right? So there was no dependent structure to describe at all. And in fact, in the definition of the process itself, it had those independent increments, i.e. observing behavior on a given time interval is entirely independent of observing the process on a later time interval. But here, since that doesn't carry over, we might want to know just how much two time intervals can depend on each other. And we're going to measure that with the covariance. So dependence of increments. So what holds is that for h between 0 and 1/2, we're going to have the increments to be negatively correlated. And for h between 1/2 and 1, we'll have the increments to be positively correlated. So what does that say on a physical level, if you like? What that's saying is that for h in the regime from 0 to 1/2, you have anti-persistence, which means what's going to happen in the future is going to be opposite to what happened in the past in some sense. And the opposite is going to hold for h in 1/2 to 1, i.e. the process is going to want to persist in whatever it was doing in the past. I'm going to plot images of the process in a moment for different Hurst indexes, or for Hurst indices, and we'll be able to see that more explicitly. But before that, let's just prove this. So if we take two disjoint time intervals, S1 to T1 and S2 to T2, what we want to do is get the covariance of the process on these two distinct time intervals. So the first thing you can check is that this computation holds, right? So if you actually just write down the covariance, it looks as follows. And then the next thing you can do is consider the map f of x given as x to the 2h. And then you can define a handful of variables, a1, a2, b1, and b2, which are going to serve as two intervals, in fact, as it's not hard to check that b2 is less than a2 is less than b1 is less than a1, i.e. you have two intervals, b2, b1, a2, a1. And then what we want to do is make some argument about the concavity or the convexity of f in different regimes of h. So as to measure how much the function has changed in those times. So you can actually re-express this covariance up here as follows in terms of f. You can write as the difference of how much f has changed on the interval between a2 to a1 and how much f has changed on the interval between b2 to b1. Okay. And for h between 0 and 1/2, you can check that the second derivative of f is negative. And so that this quantity is now going to be negative, because how much it changed here is going to be smaller than how much it changed here. And similarly, for h between 1/2 and 1, you can check the positivity of the second derivative and conclude positivity here as well. So again, moral conclusion is these two statements hold. Negative correlation of increments for h less than 1/2, positive correlation of increments for h greater than 1/2. And here's what that's going to mean on a physical level. For h equal to 1/2, this is the classical process. And you should be able to sort of convince yourself that there is no correlation on the past in this model. You can kind of see that it's not necessarily continuing what it did in the past, but it's also not doing the opposite in some sort of radical way. It seems to be behaving as Markov as you would expect. But if we look at h smaller, we're seeing the anti-persistence become more and more prominent, i.e. the amount of which it jumps in a given interval is being reflected in the opposite way in a later interval, i.e. a large spike will correspond to a large dip and vice versa. And if we look at larger values of h, we're getting persistence, i.e. whatever you were doing in the past is going to be repeated in some sense. And so you can get trend-like behavior for h greater than a half. So you can kind of see here now, maybe if you start thinking of it on a modeling level, what tweaking these values of h could be useful for, right? If you're taking these small values of h and you want to model something and you want to call it centered Gaussian and you want it to have self-similarity, stationarity of increments, as well as continuous paths, but you want to somehow quantify a very high volatility of whatever the motion is, or asset price if you like, then these large dips are probably going to be better suited. But if you want something with a more trend-like behavior, then the larger ones are. I can pause for questions here as well before I talk about the limiting cases of h. Okay.
I'm just curious.
Yeah.
Oh, I have one question. Like, I don't know this, so I'm curious. So in practice, let's say if you want to use this to model some kind of fluctuation in real life and you wanted to match your data, is there like some kind of statistics that help you estimate this parameter h?
So simulation is actually a more or less famously difficult problem with this process due to its dependent structure. So simulating independent or Markov processes is a whole lot easier than simulating dependent ones. And there's actually a lot of effort being put towards simulating the process. Like, I had watched a few talks regarding the process, and one man in particular who did an internship at Bloomberg, spending time trying to find circulant matrices, among other things, to try and simulate this data and estimate this Hurst parameter so as to model things more effectively. So to answer your question, yes, there are ways to statistically infer what h might be to fit your model, but they're all very involved.
Okay.
And in the paper, of which I will leave as a reference, they actually do talk about a simulation algorithm at the end of it, in which case they talk about the circulant matrix approach, as well as some other. Any other questions? Okay, I will proceed. So the last thing to talk about is what happens when h equals 1, and maybe what happens as we take h towards 0. So Neo actually coined this term, Gaussian beam, which I thought was a great name. And so what actually happens is when you take h equals 1, it's really easy to check that your fractional Brownian motion is going to agree in distribution with something linear, i.e. a t sitting out front, and then just a standard Gaussian sitting next to it. And so what that is for each omega is just a random linear function, 2t, 3t, 1/2 t, whatever this psi is spitting out, c is spitting out. And so we can take a look at that. Here's like for some fixed omega 1. This is what a sample path looks like. This is what another one looks like. That's what another one looks like. So these are Gaussian beams because the slopes are being determined by some standard Gaussian, and you're getting these beams. So what you can think of is, again, literally just the limiting case of what's happening here. We saw as h was approaching 1 that this persistence was becoming more and more prominent. And so actually when you reach h equals 1, the persistence is so prominent that it's very literally a positive correlation in a high school math sense. So it's quite interesting, these Gaussian beams. Now, as for h equals 0, I will note that we actually only define the process for h from 0 non-inclusive to 1 inclusive. And so the process is actually undefined for h equals 0 at all, in the sense that there is a theorem that states, and I can link the reference as well, that the existence itself of a centered Gaussian process with, let me pull it up, with this covariance holds if and only if h is between 0 and 1 actually. So what that means is you actually can't define a fractional Brownian motion in this sense for h anywhere else but 0 to 1, non-inclusive on 0. So there is a converse, and it's quite strong. So that's certainly of interest. But after speaking with a friend of mine, David, we looked a little bit at what would happen is if we took this limit, and I didn't write it out here, but I thought it'd be fun to discuss it. So with some work and the use of Wick's formula to compute the 2nth moment, you can actually show that even if you were to use that formula and just look at h really small, that you get discontinuity of sample paths. And so what you can think of that as saying is that this anti-persistence gets so rough that the thing kind of splits in half in some sense. So it's very weird. It's hard to visualize, but for our sake, you can think of h as sufficiently larger than 0 in whatever sense you'd like. Okay, so those are the limiting cases, and I think the last thing I want to touch on is developing a stochastic calculus for this process. So we have the famous Ito calculus for that of semi-martingales, but the one fact that's actually a very key fact of this process that I didn't touch on here, as this is a bit of a digression into maybe a bit more of an advanced topic, is the fact that for h not equal to a half, this process is not a semi-martingale. And so all of the famous Ito calculus doesn't actually apply here. And so if you would like to describe physical systems using a stochastic calculus for this process, you have to derive a new one. And so a lot of work has been put towards that in the last 60 years or so, and there are a few approaches. There's the Young integral, as well as the, believe it's pronounced Malavian calculus. This is another form of stochastic calculus that's used on these processes, and you can get stochastic integral representations of these in terms of normal Ito integrals, but that's just for existence purposes. But in the sense of doing stochastic calculus to work with these, the standard calculus doesn't work, just due to the fact that when h is not equal to a half, it's not a semi-martingale. So that's effectively all I wanted to touch about here. Any other questions? Okay, thank you very much.
Let's thank Mathew again.
All right. I'll stick around for a little bit.
Actually, first thing we should do, I will give you a 3-minute break, and I will post in the chat a link to a survey. This is for the benefit of the speaker, your feedback. So I will put that in the chat now. Just a second.
If anyone wants me to go back to a given slide, I can do that as well. Just feel free to put it in the chat.
I have a question about taking the limit as h goes to 0. Let's say if you drop the condition that it's a continuous process, it is still able to
okay, there's the link.
Kind of take some kind of limit if you drop that assumption.
Great question. Me and David didn't look into it, but I'd be interested to see that. I mean, we did know that you would not get whatever you would get would not be continuous. But so it wouldn't be a fractional Brownian motion in that sense, of course. But
right.
You're asking what might be interesting about that limiting process. If we say, we'll consider a Gaussian process that's not continuous and has covariance given as this when h goes to 0, that's a process you can study. But you'll actually see that if you were to just naively put kind of very literally plug in h equals 0 here, you'll get a constant. And so what you'll get is some, if you were to just plug it in like this, you get a centered Gaussian process that mean 0 as it's centered, but then also just constant covariance, which is odd. And I don't know if it'd be of much practical use in any sense. Right, because at that point, you might as well introduce any other Gaussian process you'd like and specify the mean and covariance to be identically constant. You would, in particular, you would lose all of these properties immediately. Of course, you would lose self-similarity, stationarity, increments, all this stuff. Okay.
Sorry, I'm resending the link to the survey. This should work better. Okay.
Lisa, should I stick around for the results of the survey, or will those?
No, it'll get sent to you.
Okay.
Sorry, it did go through now.
Okay. If there are no more questions, thanks a lot for everyone's time. Thanks, Lisa.
Okay, I have submitted my survey. Everybody else can.
Thank you so much.
Well, thank you.
How have you been? I haven't seen you for a while.
Well, I've been working from home this term. Next term, I am teaching at least partly in person. I'll be teaching 1301 online and an undergraduate course at UTSC in person.
Oh, so you're teaching a course here online and then UTSC is in person.
Yeah. How have you been?
Cool. I've been good. It's good to kind of be in person now again. And actually, yesterday I just chatted with a PhD student who was working at the Math Learning Center, just that some of us working together, and then he's studying algebraic topology, and and then it's very cool just listening to him talking about what he's doing. Have you still been like teaching reading courses over the summer?
I've been teaching not only over the summer, also this term. I'm teaching 3 or 4 reading courses, and I also have I have work study students who are writing up some of my lecture notes from winter 2021.
Oh,
So for use in future years, including next term.
that is cool. Because I really, like, I've heard, like, a lot of students, they reached out to me. What they asked me, like, they're interested in doing reading course with you. Maybe one of them is, I don't remember who exactly, but maybe one of them is in your reading course right now.
Well, I'll send you a list of the. I mean, there are 4 or 5 students doing reading courses. Some are undergraduates, some are graduate students.
Yeah, thank you so much.
Okay.
And I hope you have a good day.
Yeah.
See
Take
you.
care. Bye-bye.